Okay, so in this video, we want to present Cauchy's mean value theorem in a very intuitive and geometric way. So here's the statement. If f of x and g of x are functions that are continuous on the closed interval from a to b, where a and b are real numbers, and both f and g are differentiable on the open interval from a to b, and if g of a is not equal to g of b, then there must exist at least one real number between a and b such that f of b minus f of a over g of b minus g of a equals f prime at c over g prime at c. And you can see why this result is an extension of the classical mean value theorem of differentiation, right? If g of x is equal to x, then a and b are different, as g of a is a and g of b is b. And so if g of x is equal to x, then g of b is equal to b, g of a is equal to a. So the left-hand side we recover f of b minus f of a over b minus a. And on the right-hand side, if g of x is x, the derivative of x is 1, and so g prime of c will be equal to 1, and we recover f prime at c. So what we have here in Cauchy's mean value theorem is an extension of the original mean value theorem. Now how can you present this to make it so that this is very intuitive, almost trivial? Well, if you remember the idea from the original mean value theorem, we sketched a graph of f of x and we compared the slope of two lines. The right-hand side was the instantaneous slope of the function at c, so this was the slope of the tangent line to the function at some point c. The left-hand side was the average slope of the function. The problem here is that we have two functions. So if you sketch the graph of f of x and produce another sketch for the graph of g of x, and you look at both graphs of g and f separately, you will never be able to figure this out. The question is, how do you create the graph of a single function slash curve given two functions, f of x and g of x? And if you think about this, you say, well, we have two functions. If you think of an arbitrary curve in the xy plane, right, there are two coordinates. The first coordinate for the x coordinate, the second coordinate for the y coordinate. So a two-dimensional curve in the xy plane has two coordinates. What if we use one function for each of the two coordinates? What if we create, using f and g, a parametrized curve in the xy plane? That way we will have a curve that is built using simultaneously both functions f of x and g of x. So here's the curve that we will have. So let's take for the first coordinate g of x, second coordinate f of x, and we let x vary over the interval between a and b. And you can see for any value of x between a and b, you have here the coordinates of a point in the xy plane. So as x varies between a and b, if you plot these points in the xy plane, this will trace a curve. And it will be a continuous curve because both g and f are continuous. And it will also be a differentiable curve because by assumption both f and g are also differentiable. So let's sketch a graph of an arbitrary curve in the xy plane. Just for the simplicity of the sketch, let's assume that the points are all in the first quadrant, so both f and g are always positive. Again, it doesn't have to be, but just to keep the picture simple. So let's look at where the curve starts. When x is a, we have the point g of a, f of a. So the coordinates of this point are g of a, f of a. And then x evolves, so the curve will move around the xy plane until x reaches its largest value of b. Say the terminal point is here at the coordinates g of b, f of b. And you can see I've put this point with a different x-coordinate than the initial point because by assumption, recall, we assumed that g of a and g of b were different, so that the point here does not land above or below the point here g of a f of a. And now let's just trace some kind of curve connecting both of these points. Again, it will be a fairly smooth curve as both f and g are continuous and differentiable. And you can draw any sort of curve you want. You can go wild. The argument will always be the same. So let me try and make it somewhat simple, but also not entirely trivial. Suppose that is the curve being traced. Again, you can draw the curve any interesting way you want, as long as it starts here and ends here. So from the intuition of the proof of the classical mean value theorem, we connect both the initial point and terminal point of our curve. And we ask, well, what is the slope of this line? Well, the slope is obviously the change in the second coordinate divided by the change in the first coordinate. So the change in the second coordinate is f of b minus f of a. Divided by the change in the first coordinate, g of b minus g of a. And already it looks like we are on the right track, because that is the left-hand side of the equality stated in Cauchy's mean value theorem. Well, now we use the exact same argument we used in the regular classical mean value theorem. Now look at the tangent line to the curve. Imagine that this pen represents a tangent line. As you let x increase from a to b, the tangent line will move along the curve, and there will be a point when the tangent line is parallel to this line. Therefore, the slopes will be the same. And you can see it doesn't have to be a unique value. Here's a second point where the tangent line would be parallel to this line, therefore, again, having the same slope. And there could even be a third point where, again, the tangent line is parallel to this line. The key is that no matter how you sketch the curve, there will always be at least one such point. Let me pick this one. I will try and make it look somewhat parallel. Now we have the tangent line at some point C. So the coordinates here are of course given by g of c, f of c. For some value of c between a and b. Clearly not a and not b. And now again, the slope of this line, choosing c just right, will equal the slope of this line. So we ask, of course, well, what is the slope of the tangent line to a parametrized curve in the xy plane? That is an interesting question. Well, the slope of the tangent line will, of course, be an infinitesimal change in the second coordinate. This is df. Right, that is what d represents, an infinitesimal change in the second coordinate divided by an infinitesimal change in the first coordinate, which is dg. And we want this ratio to be evaluated when x equals c. Okay, that's not very useful. How do we evaluate this infinitesimal change of f and g at x equals c? Well, let's use the differential, right? We know that the differential of f is simply f prime of x times the differential of x. And the differential of g is, of course, g prime of x times the differential in x. You can also look at this as an infinitesimal change in f is given by the slope of f times an infinitesimal change in x, and similarly, an infinitesimal change in g is given by the slope of g times an infinitesimal change in x. And again, we evaluate this ratio at x equals c. Of course, obviously, dx over dx cancels, and we are left with f prime of x over g prime of x being evaluated at x equals c. And now if we evaluate, we get the derivative of f at c over the derivative of g at c. And now we have the desired result. Choosing c just right, the tangent line to the parametrized curve in the xy plane will be parallel to this line. And since they are parallel, they will have the same slope. And so f of b minus f of a over g of b minus g of a will be equal to, for some choice of c, the derivative of f at c over the derivative of g at c. And this completes the geometric proof. And again, no matter how wild of a curve you sketch, you will always find at least one such point. So hopefully this makes Cauchy's mean value theorem much more intuitive.